Throughout history, physicists and mathematicians alike have always pondered as to what the coldest type of substance could be. But it really wasn't until the mid-20th century that the Bose-Einstein condensate was found, deemed to be one of the most coldest substances in the known universe. Within this state of matter, the particles use so much kinetic energy that they start to clump together and condense, forming as individual waves rather than individual particles themselves, and reaching temperatures well near 0 degrees Kelvin. In order to achieve such a state, rubidium-87 lasers are typically used in order to take away the kinetic energy, or in this case the heat, that's transmitted by these particles. And these particles in the long run act much more like bosons than they do as regular matter lattices or fermions. To picture this scenario nicely, imagine that you have a boiling pot of water. Within this boiling pot of water, you then put a lid over it. You notice that the water molecules start to condense and rapidly evaporate, and as they do so, they start to clump together and form condensates. In a similar light, the Bose-Einstein condensates work in the same way, in which the cold particles start to clump together and act as one group rather than individual particles themselves. Now, the history of the Bose-Einstein condensate is quite interesting. It first started off with the theoretical calculations made by the Indian mathematician Satyendra Bose, who later on sent it to Albert Einstein, who saw those works as being very applicable and later on published those works in his later life. However, it really wouldn't be until 1995 that thanks to some MIT researchers as well as Eric Cornell and Carl Wyman would we see that Bose-Einstein condensates can actually form in a laboratory environment, and was later demonstrated again in 2018 in the Cold Atom Laboratory in NASA, who found out that the Bose-Einstein condensates can exist freely in space without the requirement of magnetic fields. Now let's ask the question that everyone really wants to know. Why do Bose-Einstein condensates actually matter? Fortunately, because of the fact that Bose-Einstein condensates have many quantum applications, such as being able to quantumly tunnel, understanding them more gives more glimpses into the atomic realm, into the subatomic properties of atoms, as well as what the quantum world really does. And in the long run, it gives us more insight into lithography, gravitational fields, and lasers that should impact millions across the world. However, there's simply not too much information that we know of when it comes to Bose-Einstein condensates in the status quo. However, researchers are continually working on it, and they're discovering new things every day. Who knows? Maybe one day it will become the next revolution.